Thank you for joining. For this session, we're talking about .NET 6 performance with ARM64 using the AWS Graviton2 processor. My name is Kirk Davis, and I'm a Principal Solutions Architect on the Application Modernization Labs team. And joining me a little later in this video is Carlos Santos. He's a Senior Solutions Architect on one of our Specialized Solutions Architects teams. So different types of CPUs can use different chip architectures and instruction sets. The two main instruction sets we see in servers these days are typically x86 or x86-64 or x64, which is the 64-bit version of that architecture, and ARM64, which is the 64-bit version of the ARM architecture. Graviton2 is an AWS designed CPU that's offered in some of our EC2 instance families. These chips are designed by Annapurna Labs, a subsidiary that we acquired in 2015, and they're based on the ARM Neoverse N1 architecture, which is optimized for high performance and for use in data centers. The 2 in this case refers to this being the second generation of the chip, and it's substantially faster and more capable than the first generation. The original Graviton was launched in 2018 in the A1 instance family, and that was done partly as a way to seed the ecosystem for the chip. So that let software developers and partners, learn to build and build on ARM and come out with the right tool sets and things like that. We announced the Graviton2 at reInvent 2019, so about 2 years ago. And then over the course of the following year, we launched new instance families based on that chip. The Graviton2 powered instances, they use the new naming scheme. So there's a G appended to the end of the base name. So there's a T4G.xlarge or an M6G.2xlarge. The G is for Graviton. The same thing we did for AMD processors where there's an A. So if you see a T3A, that's going to be an AMD powered instance. And we actually have moved to that also with the new Intel powered instances too. So for instance, in August, we launched the M6 series based on Intel processors. So those are M6i.2xlarge and M6i.4xlarge and so on. In general, across the board, actually, the Graviton2 based instances are less expensive than their x86 based comparable instances. And yeah, so that's how you can tell the difference. The cost difference is about 20% versus the Intel processors, and it's about 10% versus the AMD processors. And I'll talk more about that in a second. I wanted to show a couple headlines that just from over the last year. So most of you probably already know that ARM chips have been really spreading through the IT landscape. There have been Windows laptops actually running on ARM for about half a decade now. And the new MacBook Pro from Apple runs on the M1 processor and now the M1 Pro and the M1 Max. And those are ARM system on a chips also. And we've also seen that ARM processors are moving into the data centers. And in the cloud, we've seen at least one other public cloud provider joined AWS this past summer in offering ARM-based virtual machines. And we expect others to follow. And the big reason for this is efficiency. ARM chips deliver more power, more performance per watt. And this means that, in your mobile devices, batteries last longer. But in the data center, it means that the servers need less electricity and less cooling. And the reason they need less cooling is, less power in means less power being dissipated as heat out of the chip. So that's one of the reasons you're seeing this spread into the data centers and in cloud providers. Just like the other EC2 instance families, the Graviton2 powers different instance types that are optimized for compute, memory optimized. There's general purpose, including the new burstable instance types that are T4G instance family. And you can find more details on the specific details of each of these optimized instance families and the use cases that they're set for or they're ideal for by looking on our website. So at a high level, I'd like to point out a couple of differences before we dive into the more technical content. The Graviton2 instances, like I said before, they're about 20% less expensive than the Intel-based x86 instances and about 10% less than the AMD. And that's for straight EC2 costs. So I pulled some comparative costs. These are from last month from the Ohio region but you'll see the same pattern across all of our regions and instance types. If you look at managed services that are built on EC2, like RDS, which is our relational database service, the difference in price isn't quite as great because you're not just paying for the raw compute, you're also getting automatic backups, automatic database engine upgrades, and operating system maintenance, and a lot of other things. But they're still less expensive, and they're really popular with customers running open source databases like MySQL and Postgres. The other big thing I wanted to point out is what the difference is in what a vCPU means. So for the Intel and AMD based instances, a vCPU refers to a logical core. Now Intel calls that a hyperthread. AMD has their own nomenclature for this, but essentially each physical x86 core can run 2 threads at a time with very little overhead and context switching back and forth between the threads. But with a Graviton2 instance, each vCPU is a physical core. So if you have an instance type, say, that has 8 vCPUs, if it's based on Intel or AMD processors, that's going to have 4 physical cores and thus 8 hyperthreads or 8 logical cores. But with a Graviton2 instance with 8 vCPUs, there's 8 actual physical cores. So keep this difference in mind if you're manually allocating threads in .NET or manually setting the max size of the .NET thread pool. I wanted to give a quick shout out to some of our customers that are running Graviton2 processors. We have lots and lots of customers that are running Graviton2. You can see a bigger list by going to aws.amazon.com/Graviton2, and you can slide down to some of the customers. Any of you with teenagers probably recognize the Snap logo. For me, I'm more interested in the Datadogs and the Circle CIs, but we have lots and lots of customers, many customers I've worked with personally that are moving on to Graviton2 for the performance and price benefits. So .NET on Graviton2, it kind of first became possible with .NET Core 2.1, but the first version of .NET Core to support the SDK was 3.1. And then with .NET 5, a lot of performance improvements were made for Arm64 specifically. And then .NET 6 went a little farther, improved that Arm64 support, and also filled out the Windows on Arm support, and then includes native Arm support on Mac OS also. So if you are on one of those M1 powered MacBook Pros, you can use the native Arm64 .NET 6 SDK now. You don't have to run that in emulation mode. Note that we don't actually offer M1 based Mac EC2 instances or Windows on Arm EC2 instances. So that would be for your dev environments. We do actually have Mac OS EC2 instances, though, that we launched a year or two ago. Also with .NET, keep in mind that every other release is a long-term support release. So currently that's .NET Core 3.1 and .NET 6, and then eventually .NET 8. And then the alternate releases are considered current releases. So those have shorter support timelines from Microsoft. With .NET 3, support was added to .NET for hardware intrinsics, but only for x86 processors. And that let .NET code take advantage of hardware instructions that are actually in the x86 processors, and that really all modern CPUs support. And with modern CPUs, some of these things are implemented in hardware, which means it's a lot faster than doing the equivalent thing in software. Because modern ARM CPUs have this functionality also, .NET 5 introduced support for directly using those hardware features to get better performance. These APIs are accessible through the system.runtime.intrinsics namespace. So there's one in there for .ARM and one for .x86. There's more than 350 of these ARM-specific APIs. Most of them deal with vector values and vector manipulation. But Ryujit, which is the just-in-time compiler for .NET, was also updated to emit the right ARM-specific instructions. And then there's assorted .NET classes there in the middle on this slide. They're in the system namespace. They're base class libraries, really. And these were optimized to use those intrinsics. And so with .NET 6, there's been additional optimizations as well. So the takeaway is that if you're using any of that code or any of the APIs that rely on that underlying code, you should see better performance with .NET 5 and .NET 6 than you did on .NET Core 3.1. And .NET 6 honestly has a lot of other performance improvements as well. Finally, starting in .NET 5, ready to run ahead of time compilation supports pre-compiling methods that use these intrinsics. So even if you're pre-compiling your app so that it cuts down on the just-in-time compilation time when your app starts up, you'll get that same benefit in the app, right? So also the optimizations that were done for ARM mean that the emitted assemblies are smaller, and so they're smaller and they have less code, which means when your app starts up, it starts up that much faster. In September, we added support for ARM-based Lambda functions, which run on Graviton2. These ARM-based Lambda functions get a 20% discount on duration charges, which is how our serverless platform called Lambda actually does the billing. It's done in milliseconds of how much time the functions take to execute. So we'd really encourage you to take a look at the performance of your Lambda function on ARM versus x86, which was the sort of previous default. And if you're getting the performance you want from the ARM-based Lambda function, that's an easy 20% savings for your organization. Currently, at the time that this video was recorded, we don't yet support .NET 6 as a managed runtime in Lambda, but we expect to add support for that in the near future so that you'll be able to deploy .NET 6 functions directly to Lambda without having to use a custom runtime or packaging it into a container, which is what you would do right now. If you want more details on running .NET Lambda functions specifically on ARM, please check out Norm Johansson's GitHub page. There's a link there in small gray at the bottom of this slide. And he has sample code and instructions and additional detail on ARM-based Lambda functions in AWS. And then finally, if you're looking at your Lambda functions in the AWS console, we've added a new column to show the architecture. If it doesn't show up by default for you, you can use the little gear icon and then pick the column so that it then shows up. You can see the example here. I have an ARM-based Lambda function at the top of that grid. Next, I wanted to do a demo where I launched an EC2 instance with the .NET 6 SDK on it. And then I wanted to show how you could use that EC2 instance, which will be a Graviton2 EC2 instance running the .NET 6 SDK. I wanted to show how you could use that as a development environment, because one of the questions I get sometimes is, well, if I'm building on a laptop that's running an x86 processor, how do I know my code's really going to run on an ARM processor? Or what if I want to debug on an ARM processor in C, right? So you can actually use a Graviton2 EC2 instance as a remote development environment using VS Code and then an extension to VS Code called Remote SSH. And so I'm going to demo that now. So let's go ahead and see what that looks like.
So now I'm on the AWS EC2 console on the dashboard. And so I'm just going to go ahead and launch an instance. And I'm going to pick Ubuntu server just because currently that's the one that is the easiest to get the .NET 6 SDK up and running on. By the time you watch this video, we may have the same easy process set up for Amazon Linux too. Ubuntu server, so 20.04, that's fine. Notice that I pick 64-bit ARM, hit select. This will show me the different instance families I can pick from. We don't need anything big for this demo. I'll pick a T4G micro. There's a free trial available for that. I think I've already exceeded the free trial, but you never know. So I'm going to scroll down. These are all the instance details. You can configure all of this stuff. I'm going to leave everything pretty much as it is. It'll have an automatically assigned public IP address. I'm just going to scroll down to the user text field, and I'll paste in a bash script that all this is going to do. You can see it's going to install the .NET 6 SDK for ARM64. It's going to curl down the bits, install them, and then set the .NET root path and environment variable. All right. Next, storage. In this case, 8 gigabytes is fine. We're not going to be building any really big app on this. Best practice, always add a tag so that for this one, I'll say purpose, and I'll just say reinvent demo recording. And then next, we'll go to the security group. The tag I just added will show up later, and I can look at this and look at the tags and go, oh, that's what I was doing. The security group controls the inbound and outbound traffic to my instance. I have a security group that I've pre-configured called reinvent demo SSH. This allows me to SSH in from where I am now, as well as using a feature called EC2 Instance Connect, which I'm going to demo in just a couple seconds. And so my configuration is not eligible for the free tier, probably because I'm already using too many instances. Reinvent demo SSH is open to the world on HTTP ports, which is what I want. I've opened up ports 5,000 to 5,200, which is, we'll use that for the demo application we build here in a few minutes. So I'll click launch. I'll pick a EC2 key pair, acknowledge that I have that key pair, and click launch. So now that instance is launching. When it boots up, it's going to run that script that installs the .NET 6 SDK. I do want to point out that you wouldn't have to do this every time if you don't want. Now, if we go to the one that we just launched, here it is, T4G Micro. I can scroll over and see that it was just launched right now. I'm going to give it a name. This is just another tag that's name and value, so that the tag key will be name and the value, we'll call it Kirk Demo. And I'll click save. Okay. So as I was saying, you wouldn't have to run the user script every time if you didn't want. You could just create an image out of this. I could come down to image and templates and click create an image, and that would create an AMI in my account that I could use to launch additional instances with the .NET 6 SDK already on it in the future. In this case, I'm going to click connect. There's different ways we could connect to this. I'm not going to use the serial console or even session manager in this case. The two main ways people connect to these EC2 instances would be typically an SSH client is the main way. There's also a built-in web-based SSH client, which I want to demo just because I think it's cool and it's super useful if you want to just quickly hop on to an EC2 instance and make sure that it's up and things are on there. So I'll click connect with that. It's going to open this up in a new browser window eventually. And in the browser window, I'm now in there. It's just like I was SSH'd in. I can look up here and it says ARch64. That's ARM Architecture 64. If I come down here, I have, I'm at the bash prompt. So just to check, we'll see .NET version. Did it get installed? Yes, 6.0.100. That's the version that was current at the time of this recording. So let's go ahead and create a simple app real quick before I demo the next part. So we'll do .NET new MVC and we'll call it demo MVC. And so now if I do ls or ls demo MVC, you can see that the full project is in there. Now, it's not very convenient, using a web-based SSH terminal to actually try developing code in. I guess I could use Vim or VI or Nano to edit these files. That's not really super convenient though. So what we are going to do instead is we're going to go back to the SSH client window, and I am going to copy the SSH target here, and I'm going to concatenate that with the path to my SSH, to my key pair file. Then we'll switch over to Visual Studio Code. Now in Visual Studio Code, I have the Remote Explorer extension installed. That means I can connect to remote servers. I have one in there that was already set up. So let's go ahead and add the server that we just launched as a remote server. And we're doing this because it enables us to use that remote server as an actual development environment. Because, well, let me go ahead, and while that's connecting, you can see all I did was put in the SSH command with the path to my key pair, and then the full username and domain name of the instance. I'll have it update the SSH config. It'll add this to my known. I can actually open that file up and give it a more friendly name. So right now, by default, you can see if I expand this out, it's just the domain name of the machine, but I could call this instead, my MVC demo Graviton2, and do file save. Okay, so if I come and refresh this, that'll show up. So if I want to connect to this now, I can connect to this in the current window. It's going to ask me to choose the platform. So this one's Linux, I already know. Are you sure you want to connect to this? Yes, I'm sure. So the reason you might want to do this is if you're developing on Windows and deploying to a Graviton2 instance, you might be a little wary of having some incompatibility where something runs on your Windows machine but not on the Graviton2 instance. So this is an easy way that you can use a Graviton2 instance and use that as a development environment or as an alternate development environment. You can troubleshoot, you can run your code, you can attach a debugger there. So let's go ahead now and look. So we're connected to this this environment now, the remote server. Let's open a folder on that server. You can see that the app folder that I created, demo MVC, is there. So let's pick that and say OK. And then this window is going to reload, and it's setting through. It's going to ask me whether I trust the authors of the files in this folder. Those authors are me, so I'm going to trust everything. I trust myself most of the time. All right. So if I close the Getting Started tab here, here's all of the, here's all of the boilerplate app that comes with an ASP.NET 6 app. You'll notice there's no startup.cs. They've gotten rid of that in the project template in ASP.NET. On .NET 6, everything is now just in this program file. While I'm looking at the program file, I'm actually going to take out the HTTPS redirection because we're actually going to run this and show that it's just like doing an ASP.NET app on any other instance. So I'll turn off the redirection and the HSTS stuff. Then let's look at the startup, the launch settings. By default, it listens to localhost, but if we're going to hit it from the internet, I'm going to need to change that to listen to every IP address. And we'll do, let's see, HTTPS, we'll put it 5001. And we'll put HTTP at 5,000 just to be easy. And then I'm going to I think that's it. It would run right now just to show that we're going to be doing something. I will go add, I guess I'll add a little something to let's do H1. And we'll add a little message to ourselves here that says, hey, I'm on Graviton2 ASP.NET on Arm64. We could actually dump the architecture to the screen, but I don't think we really need to go that far right now. So let's leave that be. And if we do view terminal, so now we're actually up there, right? We're in that folder on the remote server, so I can do .NET build, and that's going to build my app. I could have just done .NET run directly, obviously. While that's building, we'll come. Okay, so now let's do it. Let's do .NET run. It should be listening on all the IPs. Keep in mind it's listening on 5000 and 5001. Whoa, my mouse suddenly is slowing down. So let's go see if we can hit it. We'll do HTTP. I don't have any certificates, so I'm sure Chrome will complain if I did the HTTPS. So if we go to there, and there it is. Hey, I'm on Graviton2, ASP.NET on Arm64. So that's really how easy it is to use Visual Studio Code as your IDE with a Graviton2 or an ARM-based server as your remote development environment, and that lets you develop, test, debug your code, actually on an ARM-based instance if you don't happen to have a Windows on ARM instance locally. So the other thing I did want to show was launching or deploying a Lambda function, a .NET Core Lambda function onto an ARM instance. So for that, I'm going to do File, New, Project, and this is in full Visual Studio because I wanted to show off the AWS toolkit. I'll pick AWS Lambda project. This is just going to be a predefined project for AWS Lambda. You can get that project by either installing the .NET templates from the command line directly, or if you install Visual Studio, if you install the AWS toolkit for Visual Studio, you'll get those templates all that way. So I'll click next. We'll just call this Graviton2 Lambda, and have it go into my Visual Studio 22 projects folder. Click create. When I click create, I'm going to get a choice of different boilerplate blueprints that I could use. If I wanted to do, now we don't have one that's published at the time of this recording, which is a few weeks before reInvent. We don't yet have one for .NET 6 for custom runtime because .NET 6 just launched. We will be adding support as a managed runtime for .NET 6 to Lambda in the near future. So at that point, you'll just be able to pick empty project. It will default to .NET 6 if you have that on your system, and then you'll go from there. I'm going to pick empty function for now. And click finish. This is going to default to .NET Core 3.1 just because that's the version that's currently supported at the time of this recording. With AWS Lambda, we support long-term support releases of .NET. So that's .NET Core 3.1, .NET 6, and eventually .NET 8. You can use other versions with a custom runtime, and that works also. It's also easily supported through the Visual Studio toolkit here. So keep in mind that you'll do the exact same thing I'm doing here. The only difference would be that you'll be on .NET 6 automatically. So with that said, if I come into this function, this boilerplate empty Lambda function it's just returning an uppercase of whatever input that you put in. I'm going to replace that with a message that dumps out the architecture that it's running on. So I'll grab, let's see, I have to add the using statement here. Thank you, Visual Studio. I'll just grab the CPU architecture and the operating system architecture, and we'll return those and just ignore the input here. I'm sure that you can already guess that this is going to be ARM64, but that's okay. So let's go ahead. I'll make sure it builds before I deploy it. Not that I need to because this code's really, really simple, but it's going to get built when I deploy it anyway. Then using the toolkit, you can just right-click and say publish to AWS Lambda. In the publishing wizard, you have a choice under architecture for x86 or ARM. I'll pick ARM. We'll give our function a name. I'll give it the same name as the project just to be easy, Graviton2 Lambda. I'll put demo, I guess, here. Notice that it's .NET Core 3.1 right now. As soon as we have support for .NET 6 in Lambda as a managed runtime, that will show up here. And it is possible to run .NET 6 in a Lambda function already, which Carlos will be showing you in his demo in a bit. So I'll click next. And eventually, I can give it a role. This is just, I want to give it permissions to be able to talk to CloudWatch. So I could do basic execution and create a new role. I've already got some roles that are doing this. So I'm going to pick this one, Lambda execution, because it'll be a little bit faster. It won't have to wait for the role to propagate across. So we can see that all it's doing is it's invoking .NET publish. It's going to get that publish output and zip it up and then upload it. So that's already deployed. So if I can switch back to the browser and go to the Lambda console, and if I hit refresh now, we should see Graviton2 Lambda. Notice the architecture is ARM64. If that column's not showing up, like I said before, you can add it from the column picker. So you can see I have 2 of these are on ARM64 and the rest are on x86. If I come back to here, I can actually run this Lambda function from here. I can put in anything. We're ignoring the input, if you recall, and it's returning back to me. The process architecture is ARM64. The OS architecture is ARM64 also. Note that I can also see this function if I come down to in the AWS toolkit. I can look at all of my resources. I hit refresh, and so now that Lambda function is here. So if I wanted to clean that up now, I can do delete, and then that would delete the function. So with that, I'm going to actually pass back over, I believe, to Carlos. Carlos is going to be demoing some CI/CD on ARM64, and then he's going to do some performance testing. And with that, I'll pass to you, Carlos.
As Kirk mentioned, Graviton2 is going to give you that better price performance. You may be thinking to yourself though, what changes does the switch to ARM introduce to my development workflow? The answer to that is minimal changes, and in some cases, no changes at all. To demonstrate that, I'll be walking you through a CI/CD pipeline that we will be switching to use ARM, and along the way, I'll be pointing out places where you may experience some of those changes. For the demo, I'll be using AWS services, but if you use other applications in your pipelines, don't take that to mean that you'd have to switch in order to start leveraging ARM in your own workloads. We'll be using AWS CodeCommit as our source code repository. Think of it as managed Git. And we'll be using AWS CodeBuild to build and compile the application. CodeBuild is a managed service with a pay-as-you-go pricing so that you only pay for as long as it takes your build project to complete. We'll look to see what it takes to start using ARM in CodeBuild so you can realize the cost savings not only while your applications are running in your target environment, but also during the build. CodeBuild is going to create a container image that supports running on an ARM processor. We'll publish that image to Amazon Container Registry. Now, that's a bit of a mouthful, so I'll be using ECR for the rest of the demo. Think of ECR as NuGet for container images. With the image published, we'll use AWS Code Deploy to deploy that updated image to the target compute service. Let's jump to the AWS console and head over to Code Pipeline. Here you can see the pipelines that deploy to ECS, EC2, and Lambda, along with the x86 and ARM flavors for each one. What may be a little harder to tell is that they all use the same source code repository. The giveaway is the same short git commit hash. What we're demoing is that you can deploy the same application using either x86 or Arm64. Not that you'd normally want to deploy the same application to all services. Let's navigate over to the source code repository. Here you can see that there's only one source code repository, and it's an ASP.NET 6 application, and is what is deployed to all services. So you don't have to take my word for it. I'll be updating the application and you'll see the pipelines kick off. Let's take a quick look at the application first. Here's the application running on an ARM processor. What I'll be updating is the build ID field, which is actually the short git commit hash. And here's the same application, but running on x86. All right, let's get started making the changes. I have the application cloned locally, and I'll be updating the host info service class, which generates the data you just saw. I'll change the build ID field to say welcome to ARM, but I'll leave the build ID. Let me go ahead and commit the change. I'll use new and improved build ID as the commit message. And with that committed, I'll go ahead and push it to the repo. Behind the scenes, I have a CloudWatch event that starts the pipelines whenever a change is pushed to the repository. Let's go ahead and go back to the AWS console. And yes, you can see that the pipelines are started. While that's running, let's dive into the ECS pipeline and see what it takes to switch to using ARM. All right, here you can see that the source repository is the code commit repo. But what we're interested in is the build project. So let's click into the build project. I'm going to open up another tab here, and you'll see why in just a little bit. Let's go over to the build details tab. And what I'm most interested in here is the image used by the build environment. You can tell that it's using ARM by looking at the image name and the environment type. So let's compare this to the x86 build. I'll open the x86 project, go to the build details, and scroll to the environment section. Here you can tell that it's x86 by looking at the image name. The actual build steps are contained in a file called buildspec, so let's take a closer look at that file. Here you can see that it's called buildspec-ecs for this x86 build. And switching to the ARM build, you can see that it's the same file name. So the same commands are being executed no matter the processor. Let's go ahead and open that file and see what's going on there. The build spec file is not very complex, but I'll walk you through what's going on. Much like in Kirk's demo where he used user data to install .NET 6, we'll be doing the same thing here. .NET 6 went GA the day of this recording, and the code build images do not have .NET 6 baked in quite just yet. As soon as they're updated, you will no longer have to do this step. I do want to make a big shout out though to the amazon.ecs.tools .NET CLI extension. If you aren't familiar with it, definitely suggest you explore it. I'll be leveraging it here to log into ECR, build a Docker image, and push the latest image into ECR, all with just one command. And here's that command. I pass in the Docker file name, the Docker image tag, and the build ID. With the build completed, an image definition file is created so that code deploy knows which container to update. Big call out here though is that there is no processor specific instructions on this file. That's why both builds can use the same file. So let's go ahead and dive into the Docker file, which is where the actual compilation is happening. First thing you may notice is that we're using a multi-stage build so that we can keep the size of the resulting image to a minimum. We're using the ASP.NET 6 runtime image as our base and pulling it from the Microsoft Container Registry. Definitely encourage you to use the registry as it will get you the latest patches and prevents you from having to manage your own version of the .NET 6 image. To compile the code, we need more than just the runtime though, and so we're using the .NET 6 SDK image for the compilation step and also pulling that from the Microsoft Container Registry. After that, it's pretty vanilla .NET. We restore the NuGet packages and build the release configuration to the publish folder, passing in the build ID. Once the code is compiled, we just copy the contents of the publish folder to create our container image. Again, no processor-specific steps here. What allows this application to run both in ARM and x86 is the any CPU configuration. Just like any CPU helped us out during the x86 to x64 transition, it is again coming to the rescue and easily enables the transition to ARM. If by chance you're specifying the platform explicitly, then all you have to do is change the platform name from x64 to ARM64. For example, if you're using ready to run because you need ahead of time compilation, you can switch your runtime identifier to Linux-ARM64. But that's it. That's all it takes to start leveraging ARM's better price performance. There are a couple of items of note though when working with ARM processors. ARM uses a weak memory model, and so that can affect lock-free multi-threaded code. To address that, you can use the volatile keyword in C# so the reads and writes to memory locations are not rearranged. If you're using hardware intrinsics, as Kirk mentioned, they're in the system.runtime.intrinsics.x86 namespace, so you would need to change to the system.runtime.intrinsics.arm namespace. Okay, by now the build should have completed, so let's take a look at the pipelines. Yes, the build has completed, and if I refresh the page here, you can see the new message. Both for the x86 and ARM64 builds. With the app deployed, I want to do a quick performance comparison of the application. We won't be using this endpoint though, we'll instead use the weather forecast endpoint. Since it's the same code deployed, it's available in both in ARM and x86. The one field I want to point out is the encrypted summary field. To artificially add load to the payload, we actually encrypt and Unicode encode the payload, and that is what you see in this field. In the test, we'll use two T-series servers, one a T4G, which is our Graviton instance, and one is a T3A instance. The A in this case means AMD. Both are 2x larges and are 64-bit. We're using AMD in this case because Kirk actually has a blog post covering .NET 5 performance differences with the Intel chip. So we're changing it up for this demo. For the load test, I'm using a tool called loader.io, which makes it very simple to simulate load. Here you can see the load test definition for the T4G instance, and it's configured to hit the ARM hosts weather forecast endpoint. Let me go ahead and start the test. And here you can see the x86 version of the test. The only difference is the hostname. Let me go ahead and start this one as well. Okay, while the test warms up, let me just walk you through what the test is doing. We're simulating load for 15 users for 90 seconds. The point here is not to find the breaking point of the application. We're just trying to do a quick performance comparison. Keep in mind that we artificially inflated the amount of work the endpoint is doing by adding encryption and Unicode encoding. So the performance differences you see in your applications will likely vary based on what your applications are doing. Make sure you test and see what kind of numbers you get. There are two numbers we want to watch: the response time and the number of requests. The x86 endpoint's response time hovered around the 290 millisecond mark. Let's switch back to the ARM side and see how it did. You can see its response time hovered around the 220 millisecond mark and was able to serve about 6,000 requests. That's about a 70 millisecond difference, which is roughly about a 25% performance improvement. That translated to about 1,500 more requests. Don't forget that the cost of the ARM instance is about 10% lower than the AMD instance. So not only are you getting better performance, you're also paying less for it. Okay, you were able to see to start leveraging ARM for your pipelines was as easy as changing the build project's image. And to use ARM in your workloads could actually be a no-op if you're using any CPU already. Or a quick flip of the platform to Arm64 otherwise. All right, I'm going to send it back to Kirk.
All right, thanks, Carlos. So Carlos just showed some of the performance advantages using that load tester IO. And actually, last December, in November, December, I did some initial benchmarking with .NET 5 on Graviton2 to compare it to EC2 instances running x86, in my case, Intel processors. I used Crank, which is the benchmarking tool used by the .NET development team for benchmarking. And I used it to run some benchmarks that it's the same code really that Carlos was just showing us. And I compared an M6G X large, which is the Graviton2 instance, to the equivalent Intel-based instance, which was an M5.X large at that time. And I wrote the results up in a blog. The URL is on the slide there. The TLDR is that the Graviton2 delivered up to 31% better performance for at least one of those APIs, and it was better across the board just in raw performance. And then I did some graphs. All of the graphs and the charts are on the blog, but this is just a subset of the sort of takeaway graph, in my opinion, which shows the difference in the performance per dollar, where I looked at the requests per second divided by the hourly cost of the instances that I was using. And so that 20% discount for the Graviton2-based instance, it sort of amplifies the difference. And here, the orange bars are for the M6G, the blue bars were the M5.X large, which was the Intel-based instance. And you can see that even in the worst case, it was still better performance per dollar, but in some of these cases, it was up to 60% better as far as requests per second per dollar that I was getting. And at the same time I was doing this, a Microsoft MVP was doing a very similar benchmarking test. He also compared AWS EC2 instances that were based on Intel to the equivalent Graviton2-based instances, and he got very similar results, with the Graviton2 just outpacing the x86 instances in requests per second and cost less. And he wrote up his results in a blog. His blog is called Azure from the Trenches. I'd encourage you to search for that and read through that. He actually did a follow-up blog comparing the same Graviton2 instances with the equivalent x86 virtual machines and another big public cloud provider that didn't offer and doesn't offer at this time ARM-based virtual machines. And he found the same thing, that the AWS Graviton2 instances just gave more performance and more performance for the dollar by an even bigger margin. So I know that we've talked about EC2, and I mentioned RDS, and we've now talked about Lambda, and we have other services in AWS that also support the Graviton2 processor, including ECS and EKS. Currently, they support Graviton2 hosts. You can use AWS Batch, which is a managed batch processing service. If you have a lot of batch jobs, you want to orchestrate and schedule out. RDS, I talked about, the database service. Amazon Elasticache, which is our managed Redis and Memcached service, AWS Code Build, which also earlier this year, we changed code build from the Graviton1 to the Graviton2 instances, so you get that better performance for your builds as well. And finally, Amazon EC2 Image Builder can also build Graviton2 EC2 instances. We are adding more services all the time, and so possibly by the time you see this video, we'll have had more announcements as well. So I wanted to wrap up a little with some other resources that we have that cover Graviton2. Some of these are workshops that you could go and do yourself if you want to learn how to use EKS with Graviton2, or use the AWS CDK to launch Razor apps with Graviton2 in Amazon ECS. You could do that. We also have a Graviton2 Getting Started page in GitHub. There's a .NET page just for that. I would always encourage you to check out the AWS.NET Developer Center. All these URLs are on the page, so just pause the video and go check them out. And then lastly, the code that Carlos and I used in this session, both the source code for that ASP.NET app and the build spec files and the other artifacts that Carlos used, and that user script data that I pasted in when I was launching that EC2 instance, those are all available in that last link. That's a link, that bit.ly link will take you right to a GitHub page. Finally, I wanted to thank you for coming or watching today's session. You can reach out to either Carlos or I at our Twitter handles, which are here on the screen. And thank you very much.